right after is to understand what induction motor is constructed that. Okay. Induction motor has two main parts. That is the stator and the rotor. There is the stator and rotor. Okay, the stator is the stationary part of the motor and the rotor is the rotating part. Okay. So if I would draw a simple construction of the induction motor, the motor, the outside part, the circular part that I've drawn, which is the outside part, it's the stator. Okay, this stator is where we feed what our supply. What are we supplying? We are supplying what we call stator windings. Okay, we are supplying stator windings. These stator windings, they are wound in slot inside the stator windings. If I always slots inside the what? The stator slots. Okay. What will happen here is that when you feed a three-phase supply, these stator windings, they create a rotating magnetic field. They create a rotating magnetic field. It is important for that magnetic field to rotate, otherwise we don't have a functional induction motor. Okay. The magnetic field is rotating because of the type of supply that we are supplying, which is three-phase. And in three-phase, we know that each phase are 120 degrees out of phase. That is what creates that rotating magnetic field. Then rotor. Let's say this is my rotor. Okay. This is our rotor, right? Here rotor, you guys, here rotor there are two types of rotors. Okay, there's a squirrel cage, there's a wound rotor. Okay, this squirrel cage is the one that does not need brushes. Okay, it consists of a bars short-circuited by entrance. As I entrance, computer a second. Okay. Remember, in order for us to have the motor action, there must be two magnetic fields. There must be a magnetic field here, then there must be a magnetic field here, armature. Those magnetic fields will interact and create a force. Okay. So let us take it as it's a squirrel cage construction. There is a guy. You have your rotor bars that are short-circuited by entrance. Okay. So what will happen as the magnetic field stator is rotating? Is okata, let's say, is okata through these rotor bars, as the magnetic field stator rotate. So if magnetic field a conductor, we know we are generating EMF. So EMF is being induced in the rotor. Once EMF is induced, because its squirrel cage construction have a short circuit, the current will flow in the rotor bars. Okay. Once the current flows in the rotor bar, that means the rotor is over magnetized because there is current flowing in the rotor. And that magnetic field here rotor is interacting with this magnetic field here is there to create a force. That is why this type of motor is called a what? An induction motor, because umbani is not actually supplied directly to the rotor, but is being induced to the rotor. Therefore, it behaves more like a what? A transformer. Okay? It behaves more like a what? So in fact, the energy is being transferred from the stator to the what? To the rotor. The energy is transferred from the what? Stator to the rotor. Okay. Electricity is being induced from the stator to the rotor. That is why we call this motor an induction what? Motor. This is just to kind of remind you, because this is something that you're supposed to know. This is something that you're supposed to know right now. Yeah? Okay, that's the basic that I wanted to introduce first before we start attempting to do S calculations. Okay, before we start attempting to do these calculations, then moving on here, guys, I want us to talk about two things. Okay, we see that there are two things that are rotating our induction motor. You know, the magnetic field is static. The magnetic field of the state is what? Rotating. And also any rotator, the rotor will start what? The rotor will start to rotate. So, in that case, that means there are two types of speed that we are going to talk about. That is, the first one is the non-synchronous what? Speed. That is the speed at which the magnetic field is what? Rotating. Yeah? That is the synchronous speed. Number two, your rotor what? Speed. The speed at which the actual rotor is what? Rotating. Yeah? Okay. This synchronous speed here, guys, we calculate it as what? Over P. That is something we are supposed to know. Synchronous speed is always 60 times what? The frequency and the pole what? Over pole pay. Okay? The next thing is, how do we calculate the rotor speed? Mostly when we want to calculate the rotor speed, we use something we call slip. Okay? This thing is the difference in speed between the synchronous speed and the what? Okay? And that is, the synchronous speed is always greater than the rotor speed. And they are never what? Equal. Otherwise, if they were to be equal, the motor won't operate. Yeah? Okay? It's not practical. Okay? Slip is the difference in what? In the synchronous speed and what? Rotor speed. Rotor speed is measured as a percentage value. Slip is a ratio calculation. Ns minus Nr over. Okay? Okay. In ways when you start your motor, how motor you have to start, remember the rotor speed. The rotor speed remember. So if we know Ns minus 0 over Ns, it means, guys, 1. That means at starting, slip at starting, you should not be. You should know. Slip at starting is equal to 100 what? Percent, because the rotor speed at starting is what? 0. At starting or at what? At state, Okay, slip is what? 100%. Starting or at what? Standstill. Okay. Yeah. Now I cousin will possible because we cannot have synchronous speed be equals to rotor speed. Because the rotor speed means that the synchronous speed and the rotor speed are equal. That is what it means. Now we are going to talk about how does the energy moves P the induction mode. Okay, and there are three types of losses as is what There are three types of what? Ion loss, okay. Ion loss is due to magnetism, okay. Then big copper what? Copper loss. Your copper loss is due to a current flowing through a resistance. I squared R plus, what you call it. Then you make friction and what? 1H loss. That is mechanical. That is what? The only loss that I've mentioned, that is electrical, copper loss. The iron loss and the friction and 1H loss are not electrical. And this is an electrical subject, and you don't have formulas to calculate iron loss and friction and 1H loss. Okay, some you will be given, if the question wants you to consider. Okay, or you want to copper loss, copper loss is I squared by R. Okay, that is stator losses, guys. In order for us to calculate efficiency, we must know what are the losses. Now you will see that when we get to N6. Okay, but how does the energy flow? Now we're going to talk about energy. Energy flow diagram. Induction mode. Guys, let's say supply state. That means the input here motor is state. So if you look at that diagram there, what is input? The color state, okay. Does this data move? Does this data have a moving part? No, that means this data I equal friction and what? While is what? Loss. With data. There are two losses with data. That is the ion and copper loss. Okay, there is more here. We are rotor. But look what is happening here. We have more like the output. Yes, data is equals to stator input. Stator what? Stator output is equals to rotor, sorry. Stator output is equals to rotor what? Input. And what your stator input is equals to input power. Is that input power? Stator output is equals to rotor input. And number rotor again, there are two losses per rotor. That is the what? Ion and what? And copper loss. Ion and copper loss. Now go rotor. After you rotor, Certainly, we're bearings. After rotor, bearings. This is where we get only a friction loss. We don't have the iron loss and copper loss here. We have only friction what? Loss. Okay. So a rotor output. The input will only the bearings. Rotor output. Okay, no, don't take it like that now. A rotor output, and also guys, a rotor output can also be called cross what? Output. Please don't confuse the rotor simply out. People they can confuse power out, no rotor, output. I only one. Power out, no rotor out, no rotor output are not the same. Or rotor output is the what? Cross output or a power developed. Upri out after we have deducted, the friction and what? And what? One is what? Loss. This is the power developed. Power out here, power developed. With power that is being developed. But friction and what? One is what? Loss. After friction and one is loss, we can say we have our what? Output what? We can say that we have our output power or our net what? Output. Okay. So guys, there with this diagram we can work going towards that direction and from the input to the what? Or you can work from the output to the what? Depending on the what? Question. Depending on the question. Depending on the question. Now let us look at for a calculation for a induction mode. What is important also is remember your star and what? Delta configuration. And I always stress this, a given voltage is always the line what? Voltage. A given voltage is always the line voltage. That does not change. Okay? Now the power is connected in delta. Phase voltage is equal to the what? Line voltage. If it is connected the star, the phase voltage is equal to the phase voltage is equal to the line voltage over the square root 3 and star. Okay? And also you know impedance. Impedance per phase R plus what? Remember, motors are what? Motors are inductive. Motors are inductive. Motors are inductive. And one for ohms law, P phase 1 is equal to P phase 1 over P1. Okay? And alpha is the impedance is into. This data has its own what? Impedance. And because it is made of what? Windings. They are stacked windings. The rotor now in impedance. Yeah, okay. This data copper loss is about data copper loss. Copper loss. Remember the only losses we buy are copper loss. Okay, as the losses they will be what? Given if the question wants you to consider that. Yeah? Is data copper loss is equals to 3 squared P phase 1 over P1. Like 3 multiplied by is because the number 3 phase. Remember, we are dealing with 3 circuits with 3 wires. One is flowing in each wire. Nah? So that is why we multiply by what? 3, because we are dealing with what? 3 phase. Okay. Then it is the this is the stator over loss. Then how do we calculate the stator output, of which is the stator output? Your rotor what? Input. Remember your energy flow diagram. Stator output is the what? Rotor input. This stator output again is equals to the what? Input power and then minus losses. Minus as and losses P we state. And we state the losses as we state as an stator copper loss and iron and loss. So it's equals to value. Load of the in bracket value. Stator copper loss, of which is nonsense. That is how we calculate the stator copper loss. Minus what? Iron what? Iron loss. That is how we calculate what? The stator what? Output. Energy what? Flow what? Diagram. But since again, the way we do calculation in the rotor, it is going to be different, a bit slightly different. Because remember, a rotor can be a standstill and a rotor can be a what? Rotating. So in values of standstill, as is of another they are rotating what? Values. Okay. That is why when we're talking of a rotor, we consider standstill values and we consider rotating what? Rotor values. Okay, before I get into a rotor, what is important is how we're going to calculate. Remember, we said it was no basic analysis, but there is transformer action that is taking place between the what? Stator and the what? Rotor. As that rotating magnetic field is rotating, and then it is cutting the rotor what? Conductors, and it is inducing EMF. Operation transformer. That is why here we are going to use transformer ratio. Because induction motor behaves more like what? A transformer. Electricity is induced from the stator, which is, you can view it as your primary circuit, to the what? Rotor, which is, you can see it as the what? Secondary circuit. Okay. So V1 phase money, remember, and I've always said this, when you are working with 3 phase in calculations, we are always working within one phase what? Phase. I calculation that phase or balance line. Okay, that is why I must always what? Convert to one phase. Okay. Listen there. E2 is the rotor induced EMF per phase at what? Like is standstill what? Value. It is always the what? Standstill what? Value. Then it can go NP1 is the what? Number of is the number of stator turns per what? Per phase. Then NP2 is the number of what? Rotor turns per what? Per phase. Yeah? Okay. Then we know that OVP1 supply voltage. Yeah? Okay. You don't supply what? Voltage. And notice something here. Yeah? Alpha, nobody, R, P body, 2, and 1, SP2. Zindoni is there. It is rotor resistance at what? Standstill. Yeah? SP your rotor reactance at what? Standstill. The rotor reactance at standstill. Okay, these standstill values have to be converted. They have to be what? Converted to rotating value. How do we convert these standstill values to rotating values? This is how. To do so, simply multiply all frequency-dependent quantities by the what? The slip. We simply what? Multiply all frequency-dependent values by the what? The only value I know that is not frequency-dependent, resistance. Resistance, as we change guys, resistance does not depend on any frequency. Okay? It doesn't depend on frequency, reactance. That means the reactance I must convert it from a standstill value to what? By multiplying by slip. Let's go to the next page. And let us see which are these frequency-dependent values. And notice, if we're rotating values, it will show that to show that is a rotating what? Value. For example, in EMF, induced EMF per rotor, it is what? Frequency what? Dependent. The rate at which the synchronous or the rate at which the magnetic field of the stator cuts, if magnetic field is a stator or a synchronous speed, a stator is what? Very fast. That means more EMF will be what? Induced. Remember, EMF induced is correlated to the rate of change of what? Flux. That is according to what? Faraday's law. Okay? So EMF is frequency dependent. This is the rotor EMF, but here it's a rotating what? Value, which is equals to money. Resistance, notice the resistance I change. Yeah? Low velocity is still equals to body EP body 2 because it is not what? Frequency dependent. And this calculation says simple by N5. Okay? Then your reactance, it is frequency what? Dependent, so we're gonna times it by what? Slip. Okay? Then, okay, that means because E reactance, it is frequency dependent. That means impedance, you must also have a rotating what? Impedance value, which is 1 RP2. Remember, I changed problem in the upper here what theta A. The reactance is the one that change. Okay. Plus x p what? R. Okay. Then spelling rotor what? Frequency. Your rotor frequency is S, then your supply frequency. Whatever supply what? Frequency. To multiply the what? The slave with the supply frequency in order to get the rotor frequency. So what is that frequency for? Is the frequency of the what? Rotor current. It is the frequency of the rotor current. No? Okay. And now that I need a shorter symbol again,